In this section, we will define the chain rule. And really, you'll find that if you've been following my technique for taking derivatives, we've been using the chain rule. Our differential form has the chain rule fully embedded in it. And so I find that students that have been practicing my technique do not find the chain rule that challenging. So here's the setup. We have a function, y, and it is a composition, say, of two functions, f of g of x, say. So then we're going to make a substitution. We're going to let u equal g of x. And so we know that, or making that substitution, we know that y is f of u. So then what's the differential of y? Well, by definition, the differential of y is f prime of u du. And we could stop there, except for we know some things, in particular that u is g of x, and so we know what du is. Du, well, that's just the differential of u. It is g prime of x dx. And so using that, we put this in our function, or our equation here, and so this is equal to f prime of u times g prime of x dx, and putting the final finishes on it, this is f prime of g of x times g prime of x dx. So this can give you a quick way. If you just see that, oh, I've got a composition of functions, then the differential of y is f prime of gx, g prime of x, or writing in the derivative form, dy dx is equal to f prime of g of x times g prime of x. And the way I tend to think about this is that if I've got a composition of functions, f is on the outside, so it's my outer function, g is on the inside, it's my inner function. So then when I take the derivative of a composition, it's the derivative of the inner function. This is the inner function, and this is the derivative of my outer function. And it's just the product of those two. You've got to remember that the derivative of the outer function is still evaluated at g, but then the inner function is just multiplied on the outside. Seeing this using Leibniz notation, we know that right up here we've said that y is a function of u, where u is a function of x. So then dy dx is just, well, f prime, that's dy with respect to u times du with respect to x. Both these are good versions of the chain rule, and depending on the situation, we might want to think about it using Newtonian notation here, that dy dx is f prime g of x times g prime of x, or using Leibniz notation here, dy dx is equal to dy du times du dx. And we will explore both notations and how they can give rise to helping us solve problems. But let's do a concrete example, and with it we'll demonstrate that you have been using the chain rule using differential forms. So we'll calculate the derivative two different ways. So y is equal to the square root of 3x plus 8. So we've got an inner function, the square root, and we've got an outer function. So we can say that maybe f of x Our outer function is the square root of x, whereas the inner function g of x is 3x plus 8. So then with that, we can rewrite y as being f of g of x. And our chain rule says that y prime is equal to f prime of g of x times g prime of x. Well, what is f prime? Well, we've done the square root quite a few times, so hopefully, this is the power rule. But f prime of x, using the power rule, is 1 over 2 root x. And g prime, this is just a nice polynomial. Again, you should be able to compute this derivative quite handily by now, that the derivative of g is 3. So that's what f prime of x is, but we need f prime of g of x. So this is equal to 1 over 2 square root g of x times g prime, which is 3, which is 3 over 2, and then what is g of x? It is 3x plus 8. So there's our derivative, 3 over 2 square root of 3x plus 8. I already said I was going to do this 2 different ways. So using the differential method, dy is the differential of the square root of 3x plus 8, which fully recognizing this as a power rule, this is 3x plus 8 to the 1/2 power. Now, power rule says that this comes down, becomes our coefficient, and it will reduce by 1. So that's going to become my coefficient, and I'm going to reduce by 1. Excuse me. So this is equal to 1/2 times 3x plus 8 raised to the minus 1/2. We still need our du, so d 3x plus 8, which is, this is, I can bring that down, and the differential of 3x plus 8 is 3, so this is 3 dx all over 2 square root of 3x plus 8. See that we got the same answer, whether we used the chain rule, which is 3 over 2 root 3x plus 8, or to get the derivative, we would divide by dx, and of course that dx would cancel. And so these two solutions clearly agree that 3 over 2 root 3x plus 8. So when we use differential forms, we were using the chain rule. So at minimum, the chain rule can help us speed things up if you can recognize composition of functions. But on the other hand, being good practitioners of the differential rules, and you follow the differential rules to the T, you will automatically compute the derivative using the chain rule. With that being the case, it is a good idea to do an example in which the chain rule does help us out and make our lives easier. So let's say that we know that y is equal to e to the u, and u is equal to the square root of v, and v is equal to sine of x. So there's a bunch of nesting going on. E is equal to, or y is equal to e to the u is the square root of v, and v is sine of x. and I want to know what is the differential of y with respect to x. What is dy dx equal to? So here's where Leibniz notation can open things up, because y is not directly a function of x, it's a function of u. So this is equal to dy du, something we can calculate directly using our differentials, times du dx. Okay, so just really paying attention to notation. This dy du, the derivative of y with respect to u, we're in good form because y is a function of u. Right? Bad writing, but that's a u. Now, on the other hand, we've got here du dx. But if we look at du, or look at u, it's not a function of x, it's a function of v. So this tells us that we need to break open this derivative one more time because v is a function of x. So rewriting this, this is dy dx times, how about dy du times du dv times dv dx. Okay, we've done this little unpacking business, and now, as we were worried about before, we had du dx, but I've rewritten the derivative of u with respect to v, which u is a function of v. And then if I look at dv dx and take a look at that function, v is a function of x, namely sine of x. So another thing I just really want you to be cognizant of, this notation is quite elegant. Remember, these are differentials, so they're infinitesimal numbers. But I've got dy dx on the left-hand side. And right here I wrote dy dx over du dx. These are fractions, and we know that when we multiply fractions, we could cancel out the denominator with the numerator because it's the same number up there, which of course this simplifies to dy dx. Now, using the chain rule, we don't want to cancel out, but the notation supports this equality, that dy du times du dx is exactly dy dx. And then, well, we expanded even further, but the consistency holds because these are fractions of infinitesimals, and this differential would cancel with that differential, and this differential cancels with that differential, and what's left is dy dx. So by just the elegance of the notation, the chain rule is exactly fraction multiplication using Leibniz notation. Okay, back to the problem. We now want to know what dy dx is. And equality says that that's the same as dy du times du dv times dv dx. So let's take a little side note here. What is dy du? Well, dy du is the differential of e to the u du, which is e to the u. What is du dv? Well, du dv is the differential of the square root of v dv, which is 1 over 2 square root of v. And finally, what is dv dx? dv dx is the differential of sine of x dx, and the derivative of sine is cosine of x. So putting all the pieces together, we get that dy dx is equal to dy du, which is e to the u, times dv du dv, which is 1 over 2 root v, times dv dx, which is cosine of x. And this is a viable answer. However, if you notice, I want to know the derivative of y with respect to x. And over on the right-hand side, I've got the variable u, the variable v, and the variable x. So I'd like to write it all in terms of x. Well, u, kind of going just substituting everything in, this is equal to e, so u is equal to root v, times 1 over 2 root v, but v is sine of x, so this is root sine of x times cosine of x. And we're almost there. We still have this pesky v sitting around, so the final answer would be this is equal to e to the square root of sine of x, because recall that's what v is, times 1 over 2 the square root of sine of x times cosine of x. And that would be our final answer.